Good morning everyone, it's again time for Advent of Code, and today is day 22 and we are getting ready to start. We have a few minutes left and I see Alex is already online, so good morning Alex. And you're mentioning that you found a shorter solution to yesterday's puzzle, which doesn't require T at all, so I would like to see how that works. Yesterday we were trying to do a little bit of code golfing and trying to make our solution as short as possible. Yesterday's puzzle was one in which we are a robot and we're walking on a horizontal line and we have to inspect every part of the line all the way till the right. But there are holes on the line and we have to jump when there are holes. We jump about 4 positions always. And the way to control the jumping is by passing a sort of assembly style code program into the robot, and that will be executed to avoid all of the holes. And so the best solution we came up yesterday, we were doing this together, was to check that either the first, second or third tile in front of you is ground. And no, hold on a second. We are checking that all of the 3 tiles in front of us are ground, and then if that is not the case, then we would jump. So we are jumping as long as any of the tiles in front of us is a hole, and tile D, where we are going to land, is not a hole, it's a ground. So that's the first bit, and let's see what this new solution looks like. So this new solution has no T in it, which means we need no temporary variable, we only need the jump variable, that's all. That is quite cool if you can do it that way. So I'm going to have to strip a bit of these characters. And so how many lines is this actually? So we'll run it and it says it is 7 lines and it takes a bit of time, and we do get the same answer as our solution got. So actually how it works is that if there's a hole at H, then it's going to jump, and also if there's a hole at J, it's going to jump. Actually no, if there's a hole at H, it's going to jump, or if there is ground at C, and there's ground at B and at A, and then in the end it's all inverted, so we should read it the other way around, like if there's ground at H, this is an OR, so then the statements the logical implication is kind of reverted, and that is a bit difficult to read. So Alex, you're saying it is basically what is written is that if there is a ground at the end, you don't have a specific case where A and B is ground, but C and C is a ground, or there's a hole at H. Yeah, so that means that if... but what is interesting is that E is never checked. So it's never checked that after landing you can't walk. Interestingly. Okay, hey, good morning G. You're right on time, because day 22 is starting and I haven't prepared my basic script. I'm assuming that we're going to open our input again, and it's not going to be an int code computer because, as kind of pattern indicates, those are only on odd days. So good luck everyone. I hope to see you after solving the puzzle, and we can look at some of the best solutions out there. Have fun. Day 22, Slam Shuffle. There isn't much to do while you wait for the droids to repair your ship. At least you're drifting in the right direction. You decide to practice a new card shuffle you've been working on. Digging through the ship's storage, you find a deck of space cards. Just like any deck of space cards, there are 10,007 cards in the deck, numbered 0 till 10,006. The deck must be new, they are still in factory order, with 0 on the top, and so on. You've been practicing 3 different techniques that you use while shuffling. Suppose you have a deck of only 10 cards, numbered 0 through 9. To deal into a new stack, deal into a new stack, this is highlighted. Create a new stack of cards by dealing the top card of the deck onto the top of the new stack repeatedly until you run out of cards, so then you have reversed it, right? Yeah, then you have reversed it. Finally, pick up the stack you've just created and use it as the deck for the next technique. To cut n cards, take the top n cards off the top of the deck and move them as a single unit to the bottom of the deck, retaining their order. Okay, so shifting a stack a few cards to the other side of the deck, to the end of the deck, to the bottom rather. You've also been getting pretty good at a version of this technique where n is negative. In that case, cut the absolute value of n cards from the bottom of the deck onto the top. For example, to cut -4, you take the bottom of the cards and put them on the top. So that is basically the same as cutting at n, the total number of cards minus n. To deal with increment n, start by clearing enough space on your table to lay out all of the cards individually in a long line. Deal the top card into the leftmost position, then move n positions to the right and deal the next card there. Yes, okay. So we're basically putting down our cards one by one from the left to the right on the table. If you would move into a position past the end of the space on the table, wrap around and keep counting from the leftmost card again. Okay, I think it just means that we go from left to right, right? Continue this process until you run out of cards. For example, to deal with increment 3, your deck and the space on the table and the current position. Deal the top card to the current position, move the current position right 3. And why do we go right 3? Is this because we're cutting? Ah, we have a certain increment of where we cut. Ah, I didn't catch that. So n is actually how to cut a number of cards, but we also have an increment that is called n. That is a bit confusing. So to deal with increment 3, you start at 0, place your deck, place your card, and then you take 3, okay? Ah, no, you go to position 3 and put card 1 there, and so on. And then, if it doesn't fit anymore, you're going to keep going on the left, you're wrapping around, and so on. But what is it about cutting then? That was unrelated then? Positions on the table which already contain cards are still counted, they are not skipped. Of course, this technique is carefully designed so it will never put 2 cards in the same position or leave a position empty. Finally, collect the cards on the table so that the leftmost card ends up on the top of your deck, and the one on the right just below, and so on, until you're at the bottom. The complete shuffle process, your puzzle input, consists of applying many of these techniques. There are some examples that combine techniques. They all start with a factory order of a deck of 10 cards. So deal with increment 7, deal into a new stack, deal into new stack, and then you have a result. Okay, and then cut. Oh, these are all different examples. Cut 6, deal with increment 7, deal into a new stack. Okay, so cutting and dealing into a new stack, those are the 2 operations we can do. And cutting has its own parameter, and dealing in a stack has its own parameter. Positions within the deck count from 0 at the top, and then 1 for the card immediately below. After shuffling your factory order deck of 10,007 cards, what is the position of card 2019? Okay, So that means we're going to have to keep track of the original card indexes. Oh yeah, of course, because the only thing that identifies them is their index. So let's do that. And now there's one open question I have. When we're dealing into a new deck, we don't use the same space on the table, right? We just basically we take off all of our cards from the deck, so we have from the table, and then we deal them onto the table. And how big is our table? This is also a question. And our puzzle input looks like this. Okay. And our table is space on the table. I don't see how much space we have on the table. Deal with increment N. Start by clearing enough space on your table to lay out all of the cards individually. Okay, so the table is the same size as the number of cards that we have. Okay, that is clear, I suppose. So let's read this input file after we save it. So day 22. So we have 2, 3, 4, 5. That means we have 4 days left of Advent of Code. Day 22 input is red, and then we're going to parse it. This is a list of lines. So the lines is filehandler.readLines, and we can split that on new lines, and then for each of them let's trim it also. Although actually, when we split on new lines, readlines already splits it. What am I doing here? So for line in, and then we'll say line dot strip. Okay. Then we want to know the instructions. So, well, maybe we can just loop over it and kind of apply our instructions as we go. I think that is easy enough. So I will start with a simple instruction set, and that one starts here. This is our first instruction set, and for that I will create an input file, example 1a. Are you in uni in the United States? No, I'm not. I am in Belgium, all across the ocean. And are you Big Squeezy? I just thought it said Big Squeezy, but I'll pay attention. Right. How is it going? Are you also working on Advent of Code, or just hopping in and have no clue what I'm doing here? So we're going to go over all of the lines in our input, and let's say that we have a table, and the table is as long as our input, right? And that means 10,007 cards long. Deck size, like this. Yeah, I double check it to be sure. You're in the uni too in the US, just dropping in. Alright, well, if you're interested, what I'm doing is Advent of Code. It's an event every year around Christmas where you get one puzzle every day, 25 days in a row. And now we're at day 22, so trying to solve or trying to implement a card shuffling algorithm. Do have a look at adventofcode.com. I'll just paste the link here and see if you can follow along. So we're parsing all of the lines, and we need to know if we are going to deal or cut. So this example doesn't have deal, or it doesn't have cut, excuse me. So if the line starts with deal with increment, then we're going to deal with an increment. And our table looks like this. It's, let's see, we need to have a range of inputs, and I will cast it into a list right away, so we don't have a generator. Alex is already done, of course, within less than 11 minutes of time. Like this. So this is our table, and if we deal with an increment, then we need to take the rightmost characters to actually to get the number of increments that we're dealing with. And I have been avoiding regexes, not because I don't know regexes, but I don't know by head, from the top of my head, how to write it in Python. So we need to do re.search, and then we can use group to find it. That's actually not that hard. So increment, I'll call it our increment for regex, the egg regex that we use for the increments. That will do a search for the rightmost digits, like this, and $sign to indicate the end of the string. And now we should be able to do a group. So we can do re.search on the line, then we should get a group out of that, like group 0, and that is our increment. Then finally just importing this name. Okay, let's actually debug that a bit to see if it works. Let's run day 22. So search is missing a positional argument string. Okay, yeah. Ah, right. What I was trying to do is actually create a regex before and then reuse it, but it's not really working. I should just do it like this, and we do re.search, and okay, so the first argument is the regex, and then we have our search string. So increment 7 is parsed correctly. Okay, now we know how to do regexes and without mistakes. And if line starts with deal into a new stack, or actually it's the literal string, so we can just do it like this, dealing into new stack. So the first thing we do is dealing with increment 7, so that means that we are going to go over all of the cards in our range. So that is from 0 till deck size, and we'll call it I just for index. And then we're going to have to add 7 each time, right? So that means I times the increment. That is going to be the new position. And we need to make sure that we're wrapping around the table so that we don't throw cards on the floor. So we do a modulo by the deck size, which happens to be the same as the table size. So that will be on the table. Table with the new... wait a second. New position, that is where we are going to place card I. Actually, I think we need 2 tables. Basically, what I want to do is not just say that position I is now at this position on the table, because if we would repeat it, we're not going to actually pick up the cards from the table as we put them before, but we would just always start with a new deck and put them on the table. So I want to have a table and a new table. New table, that is an empty array. Maybe it is actually the same as our original table size. So let's make it into a list of nones. So we repeat a list with one element none as many times as the deck size, and I don't need to force it into a list. I think that would already be a list. And the new table, that is where we're going to put our cards. And we are going, what are we going to put at this position? We're going to put the card that was there before on the table. So that is I. So that basically means I is not the name of the card, but it's the old position. Yeah, that makes sense. Okay, so now we have our table, and let's show it. Print our table. And now there was something wrong. I am using modulo, but Python thinks that I'm doing a string formatting function, so that means that I'm not parsing my group into a digit. So let's parse it into a digit. And this is the new result, but the examples all deal with a deck size of 10. So I will override it. And dealing into, we're incrementing by 7, but what we get actually is not anything like the example. Of course, deal into a new stack, that is something we haven't done yet. Wait a second. What was the difference again? Ah yeah, so deal with increment 7 just means that this is our increment. Ah, and our increment is kind of overwritten every time. So here it says now we're incrementing with 7 and then we're actually doing the dealing. So the dealing doesn't happen here, it's just a configuration. So then we can keep a dealing increment. I'll start with none so that we get errors when we didn't fill it. So the dealing increment will be that. And then if we get the instruction to deal with into a new stack, then we can actually use this increment. Okay, I'll just keep the increment as a name. And I do wanna print this statement here. So now we should at least apply our dealing twice, although I do see that it doesn't work yet. And why is that? Well, we can do debug mode. My favorite way so far to figure out why code is not working. So we are dealing with a table that has a certain size. It looks like there are indeed 10 items in it. And we have our original table that looks like all of the cards in the right order. And then the new position, let's see. So our old position is 0, so we're taking card 0 from the table. And where are we going to put it? We're going to put it in the new position, which is 0. And that is because our increment is 7 and our old position is 0, so that is correct. And then for the second position, the new position should be 7. So new table, new position should be 7. And we're taking from there the old position 1. So that means that table old position, it should be 1. That is going to be stored in the new table. Ah yeah, I know what's going on. After we sort it into the new table, we have to clear our new table and start from there. So when we're done, our table is the new table. Like that. Okay, and now when we run it, we get something that is hopefully the same as in the instruction. No, we don't. We don't get 036, we get something else. Okay. Maybe we can print it after our first operation. Oh, I see that in the two operations, actually we get the same result. So it sounds like the second operation didn't do anything. Just going to pin this debug window, maybe on the bottom or on the right, that's also fine. So we don't get intermediate output here as an example, but maybe that is what we get here. So dealing with increment 3 means we're dealing, okay. And what is deal into new stack? I think I did misunderstand it. Oh, dealing into a new stack was reverting it. That is right. Ah, I forgot that. Yeah. Okay, so dealing with an increment, that is actually applying those increments directly. And dealing into a new stack was actually reverting the table. So table is reversed table. And let's run that. Okay. We cannot iterate over a reverse iterate. Oh, wait a second, reverse iterator is not reversible? Okay. Maybe we should make it into a list? Yeah. So now, do we follow the example correctly? 03 ending at 147, yeah, that looks right. Okay, now for our cutting. So this is another example. Example 1b. This is where we're going to cut. So if our line starts with cut, then we're going to have to search for the number of cards to cut. And that is basically the same as this other regex, so I'll rename it to regex last digits. Cut, I guess, cut offset maybe. And so cutting it basically means that we're going to have a table that is based on the old table, based on 2 slices of the old table. So 2 slices, and we're gonna start at 0. No, we're gonna start at the cut point till the end, and then we're going to take the first part till the cut offset, and I think I can write it like this. And now let's see if that works. We have to do that on example 1b, and that should result in something else because I'm using... okay, hold on. The second example doesn't... Oh yeah, it cuts 6. Okay, let's see if that works. Print. That's... yeah, just like this. And we'll print. And also let's print the table before we even start. Well, table of course is just a sorted list. So now we've cut at 6, and I want to make sure that I don't have an off by 1 error. So in the examples I will have a look. The cutting is explained here. So cutting 3 means to take 0 till 3 and put it at the end. So 6 should mean taking the first 6, so 1 till 5, and putting it at the end. It looks correct. Alright, and what is actually the output that we're supposed to get? Result is 307 and so on, 96 in the end, so that's right. And now we have the example with cutting with a negative number. I don't know if Python would actually do that correctly right away. And I think I feel like not reasoning about it right now, but just trying it out. Taking the lazy approach. Cut -2, that means that our regex must also recognize negatives, like a dash before, but that is within the group still, and it's optional. Okay, with an extra R annotation you can tell Python and your editor that it is supposed to be a regex. I think that works, yeah. So 1C, how do we get it? The result should be 92 something. Okay, so I think that I'm going to override cut offset. So if cut offset is smaller than 0, then basically the size of our deck minus the cut offset, that is going to be the real cut offset, right? And then, well, let's also say by how much we're cutting to make sure that we do parse the digit correctly. Cut by -2, okay, and that means we're going to cut by something else. That means cut by 12, is that correct? No, that's not correct. We should cut by 8, so because it's a negative number we can actually add it to our deck size. Then we cut by 8 and we get the right output. So I think now that we are done and we're going to run it on the full input. And we're going to use also the full deck size. And this might print a lot of stuff on our screen. Okay. Oh, well, it's actually not that slow. It's actually really quite fast. Okay, and we need to say in the end what is the position of card 2019, and we can do that using index like this, and we get 3939. Does it work? Yeah, and it's correct. Okay, so that was part 1. That was kind of fun and not too complicated, which I like. I'll commit it. Yeah, there is my star. Day 22, part 1. Commit. Now, I guess our card deck is going to be bigger or something. Yes, just as I guessed. Nubali finished part 1. Nice, we're all doing a good job. After a while, you realize your shuffling skill won't improve much more with merely a single deck of cards. You ask every 3D printer on the ship to make you some more cards, while you check on the ship's repairs. Okay. While reviewing the work the droids have finished so far, you think you see Halley's Comet fly past. Okay. When you get back, you discover that the 3D printers have combined their power to create for you a single giant brand new factory order deck of a gazillion space cards. Finally, a deck of cards worth shuffling. You decide to apply your complete shuffling process to the entire deck a gazillion times in a row. You'll need to be careful though. One wrong move with this many cards and you might overflow your entire ship. After shuffling your new giant factory order deck that many times, what number is on the card that ends up in position 2020? Gazillion, yes. I don't know how to pronounce this number. I thought that Google was also a number, or something like that. So like a 1 with many O's. Okay. Okay, yeah, right. I see that this is going to take forever, pretty much. Well, let's see if it takes forever. So our deck size is now this. Probably we cannot even make a list that long, but we'll see. And this is how many times we need to apply our entire input. Well, I know that applying a simple operation a gazillion times is going to take long, no matter what. Well, let's see what happens. For I in range 0 till then, let's see if we have an off by 1 error here. If our repetitions would be 1, we would go from 0 till 1 and we would repeat once. So that is correct, no off by 1 error. Let's run it and maybe let's not print anything. All my print statements go out and I'll print the iteration like this. No line ending, and I'm going to do \r, which means to go to the start of the line. And by doing that, you get... Oh, memory error. Okay. So by doing /r, your cursor goes to the left of the screen and you can overwrite the same number. So you don't get like a huge list of output, but you just get one digit that's continuously updating. Memory error. Okay, but you know what? It is... Wait a second. So they made all of their cards into a giant deck, but that means that all of these cards are basically repetitions of the original space cards, right? Eric, it's not so clear, but do we have space cards that are indexed from 0 till a gazillion, or do we have space cards that go till 10,007 and then that is repeated? Well, you don't have to answer if you think it's unfair to answer that, but actually it seems like I cannot divide it by 10,007. So that means that it cannot be the way I thought it is. Sure. Not fair to answer until the leaderboard fails. Sure. Okay. Python doesn't allocate 100 terabytes of RAM. No, but I did already figure it out. It's not a repetition of 10,007 cards. So. It reminds me a bit of the FFT. Basically, you're trying an operation many times and you have to figure out if you can optimize that in some way. Okay. What we can do, of course, is seeing if we can kind of combine our operations into one single operation. Well, let's go to the drawing board and see if we can make anything of this. Yeah. So let's start with our operation that reverses the deck. We can reverse just by kind of iterating over the cards in the wrong order, right? So instead of copying the table into a new table, we'll just say, okay, from now on we're going to reverse. And if we're cutting, we have to reverse all of our cuts also. So that means, for example, let's say reverse is off. Then if we have cut 10, then that should be still 10. But if reverse is on and we are cutting by 10, then that should be replaced by something else. That should be replaced by the number of cards minus 10. That is going to be our cutting offset, I guess. So let's keep those cases here, like this. That is one thing we can do to kind of combine operations, although I'm not sure what the advantage is. The advantage is basically that we don't have a list of the entire table, but right. What I'm thinking about now is that, okay, what if we can avoid having this entire table with cards, right? What if we can avoid that? We can avoid that. We can basically go over all of the lists, all of the cards. So card 0 till gazillion, I'll call it GZ. And then calculate for each card where it's supposed to be. Where it's supposed to be. And actually, we only need to know what card ends up at position 2020. So here's a certain card 2020. And to know which card was that one, basically we should reverse apply all of our input. So let's look at our input. So we know that we ended by cutting at a certain point. And we cut at 9439. That is somewhere on the right. Cut 9439. So you know that if you cut at 9439, then that means that this whole part was actually supposed to be in the front, right? It was supposed to be here. And after cutting, we moved it to the right. So before cutting, that means basically 2020 was a bit of a higher number. It means it was 9439 plus 2020. Now we know what 2020 was one step before. And Alex has solved part 2, and we'll see if he solved it in the same way. Yeah, I guess this is how I'm going to approach it. And then when we deal into a new stack, we know that we can basically reverse or invert its position, basically the number of cards minus its position. That is the position in the old stack. And that is it. So we know card shuffling, dealing. Yeah, the dealing is something that we have to figure out also. So the deck size, I'm not going to change that. Let me actually just keep the code as it was. And I want to try if we can reverse this logic. So we have our lines, and let's do part 2 separately. This is a function part 1, and then we have part 2. Function. So this function is going to figure out where the original location was of a certain digit. And the digit that we're looking for is 2020, but I want to try it out on an example. So let's say deck with 10 cards and we have example 1A. Yeah, that is dealing with an increment and then reversing twice. That is not very exciting, but we'll have to start with something simple, right? And when we print it, we can also see what the right answer should be. So let's run this. And this is the output for part 1. So now we could ask, for example, where is card 8? Yeah, okay. Card name. Okay, where was card 8? What we need to do is go over all of the input instructions in reverse. For line in lines reversed. Like that. And now it's okay. I think I can just copy and paste this to recognize the type of instructions. Like this. And so the card position is first of all the card name, and then we're going to modify it until we figure it all out. So our first input line is 1A, that is deal into a new stack, that means reversing, right? So if we are dealing into a new stack, then we're going to reverse our position, which means that the card position is the deck size minus the card position. And I'll keep deck size also here as an argument and pass it into it. And what is the index that we're looking for? We're gonna try to do it with card 8. Okay. So card position changed into card position. Let's run it. And the first part of the puzzle I don't want to run at this point. So it changed into 8 again after reversing the deck twice. That is correct. Now what do we have? We have dealing with an increment of 7. Okay. That is a bit more tricky perhaps. How does that work? Let's go to the drawing board. So let's say we are dealing with an increment of 3 maybe. Let's have a few cards here. So this would be 0, this would be 1, and this would be 2. Now, let's say that we have this position here, and we know that we were dealing with an increment of 3. Then how do we know what original position it had? I think what we can do is... it's not so clear right away. Let's actually make a map, some kind of map. So we have 0, 1, 2, and then 3 would end up being here, 4 here, 5 here, 6 here, and 7 here. What can we say about number 0, for example? That's the first one. Why is it at the first position still? We got the new position by taking the old position and multiplying it by its position. Actually, maybe I should use letters for the card names instead of numbers, because it would be a bit confusing. Like this. So we have A, B, C, D, E, F, and G. And we were looking at card A, and the original position, or the new position for card A, was its old position multiplied by the increment by 3, modulo the deck size. And okay, so how do we reverse that? So to reverse, that's the new A prime. To reverse a modulo, I'm not sure if you can reverse a modulo really. Maybe the reverse of a modulo is also a modulo. I'm not sure. Let me look that up. Hold on, I know what to do. Let's say we do 10 modulo 3. That looks like this. That results in 1, right? So can we get from 1 till 10 in some way using the number 3? I think we can't. I think we can't. We can add an arbitrary number times 3 to get 10, yes. But how many times do we need to add it? That is something we don't know. But let's look at maybe not position A, but or card A, but card. This is not the inverse operation you're looking for. Do you mean that I'm not looking for inverse operations in general, or what I'm doing now is not the right one? I shouldn't look for the inverse of mod. You're looking for the inverse of multiply. Yeah, maybe. Okay, if that's the case. Well, let's look at B here. B is at position 0, 1, 2, 3. And if we take 3 and divide it by 3, we get 1. And you could say that is the original one. But, so that works of course, but it wouldn't work for D. So D is 2, and we can divide by 3, then we get 2/3. And that means that there was a remainder, maybe. So maybe we should... the original position of D, what was that actually? The original position was 4. So originally we had A, B, C, D, E, F, and G. So these are linked. Oh, I'm not drawing on the screen, excuse me. So I just drew this part. So our letters are in the order as they are already dealt, and then D was originally at this position, so like right next to it. And gee, you're saying your program works for the examples, but you can't get the correct answer. Oh. Yeah. Oh, and you're still in part 1, I think, yeah. Well, check your negatives. Maybe your negatives... Oh well, if it works on the examples... Hans has also finished. Very good. So we're looking at D here. So D is in position 2. And if we divide by 3, we get 2/3. But it was in position 4. And so that means we know that we have a table size, in this case, of 7. Maybe if we add a number of times 7 until we don't have a remainder, then we get a whole number. Isn't that the case? I don't know, it's just a kind of wild guess. So we do 9. 2 plus... I'm not sure why I did 9. Oh yeah, 9 is the size of our table. 7 is the size of our table. Then we divide by 3. And then we get actually 3. And that is the original position. Maybe that works. Let's try it for another one. Let's try it now for F. This was D, now F. So the normal way would be just to do 1 divided by 3, which is 1/3. That doesn't work. Then we're going to add the size of our table. 1 plus 7 divided by 3. And that is 8 divided by 3. That still doesn't work. That is, let's see, 2/3 and 2, right? 2 and 2/3, because we have 6 6/3 and then 2/3 left. 6/3 is 2. Well, and then that doesn't work, so we have to add another 7 maybe. So 1 plus 7 plus 7 divided by 3. And that is the same as 15. And 15 divided by 3 equals 5. So that means we had originally position 5. Well, I think I'm probably on the right track. Where was F originally? It was here at 4 and 5. So that method seems to work. So we have to keep adding 7s until we have no remainders. And to calculate that, basically what we can do is, what can we do? Because what was interesting was that here we saw 1 and here we saw 2, and we had to add 1 and we had to add 2. So what is the remainder when you divide 1 by 3? Is it 1? And what is the remainder when you divide 2? Oh, wait a second. I'm circling the wrong thing actually. So here we had 2. No, here we had 1 in the end, and here we had 2. But in this case I had to actually add 7 once only. So maybe it's the fact that we have 2 out of 3, which means we are short of 1/3, and we have to look at this one to multiply that one by 7. That's how many we are missing. No, I don't think so. I think not. I think not, because you cannot just decide based on the fraction, how many times you need to add a number to make it work. Because if your table is longer, like 8, like you couldn't say that if you divided some number by 3, then you could determine from that already how many times you have to add 8 to the counter to make it not a fraction. I don't think that is possible. So let me just do it in a simple way and use a while loop. So we're going to reverse the increment operation. And so what we'll do first is we'll try to divide it by 3 and see if we get no remainder. So if our card position divided by something, divided by the increment, has no remainder, then basically that card position divided by the increment, that is the new card position. And otherwise we're going to have to multiply the card position. No, not multiply, we're going to have to add to that the table size. Do I have table size? The table size is the same as the deck size. We have to do that a few times, like I'll call it factor, and take that. Ah yeah, okay, so I can actually combine that. So we'll add to the card position the deck size times a certain factor and check if there's no remainder, and if so, then that is going to be the card position. And if not, then we're going to increment our factor. So this is basically a while loop, right? So while we do have some kind of remainder, then we're going to increment the factor. And in the end, then we can just use the factor. And the factor starts with 0. Okay, so I did it all at once without trying. I don't know if it will work. Let's just go over it in debug mode. So we are now at factor 0 and we have increment 7 and our table size is 10. So let's see what happens. This apparently was 0, or it actually had a remainder. It had a remainder of 1, so that's 1/3. And our factor is increased by 1, so that means that we can evaluate this one again. Now we have a remainder of 4. So our card position, which was 8 plus 10 is 18, and our increment is 7, so this can still not be divided by 7. And probably we're going to end up with 2 as a factor. So let's run it. Now the factor is 2, and then we're done. So the card position is going to be this one. It's going to be originally position 4. Now let's verify if that is correct. So that means that 4 multiplied by the increment and then modulo the table size should result in card position 8 is what we had, right? Unless we've already overwritten the card position. Table deck size like this. Yeah, we do get 8. So it seems like that is actually correct. Yeah, cool. Okay. And now we know it, and we have some reversals going on. And when we are done, we can return or print the card's position. The original card's position was... But hold on a second. Yeah, that is the original card's position, so that means that it is also the card's name. Yeah. Okay. So that means that I am asking not exactly for the card name, but for the position in the new deck. So actually these names are reversed. So actually what we get is a card position, and what we want to calculate is the original card position, which ends up being the name of the card. Original position, and this is the current position, or maybe the sorted position. Yeah, so that's the position in the deck where it is sorted. The original card's position was this. Okay, so let's run this and see what we get. It says the original card's position was 4, and we're asking for card 8. I'm not sure what I'm doing actually. Is it right? Well, that makes no sense. 8 should be, of course, at position 8 originally. So what am I doing here? So we see, hold on, 0, 1, 2, 3, 4, 5, 6, 7, 8. This is what we're doing. We're not checking for 8. We're asking what card is here in the sorted output. So, and we say that it is 4. That is what our code is producing, and that is correct. Okay, but we need to repeat this entire algorithm, right? So let's repeat it. For I in not repeat, that doesn't exist. It doesn't exist, right? Does it? No, repeat is just our parameter. Range 0 till repeat. We can just keep going with the original position like this. Oh, but I do think that I did not implement something, did I? This is implemented. Dealing. The cutting is not implemented. So let's actually implement cutting also. Yay, G, you got part 1, nice. And what was the problem? Because you had a working algorithm already, but it didn't work on your full input. So example 1b does have a cut in it, so that's the one we can try. You read the data, but you didn't call the function. Oh, okay. How did you find out that it didn't work, or that this was the problem? Because I think if you would run it with debug mode, you tested the example again, twice. Oh yeah, okay. Yeah. So we're going with example 1b because that has a cut. And for the reversal, if we do have a cut, then how are we going to say what the input is? So let's do it on the drawing board. So we had an original list of numbers that looked like this. And we were cutting at position 2. And then what we got was basically 0, 1, 2, and 3 and 4. And we reverse them. So we get 3, 4. And we get 0, 1, 2. So if we would ask what is in position 0, 1, 2, 3, let's say what is in position 3, how would we know? If we know that we cut 2, that means that, well, the cutting position is before the position we want to know, 0, 1, 2, 3, 4. So our position that we're checking is 3. 3 is what? And so we know that because 2 is smaller than 3, then we know that we have shifted to the right, right? So that we should actually subtract something from this 3. So 3 minus 2 is going to be 1. That is going to be where we were originally. That is correct. So that's one case. And the other case is, let's say we were asking for position 1. So this was about position 3, and for position 1, after cut and before cut. For the before cut case, we have that our cutting point is actually bigger than the position we're interested in. And in that case, I think it means that we moved to the right, right? So we have to... no, we moved to the left. That means that we have to add something to our original position. So the original position is... well, the position we're interested in is 1, and then we're going to add this 2 from the cutting point, and we'll get 3. That should be the output. And of course 3 was at position 3, so that is correct also. Like here. So that's all we need to know. And then we do need to check that the cut is negative. And I want to print reverse cut and reverse dealing into a new stack and reverse increment. And I think the way we reverse the cuts is still the same. And now I'll print it also, reverse cut, and then our original position depends on whether the cut was before or after the position. So if our cut offset was smaller than our original position, then we're going to add it, original position plus cut offset, and otherwise, well, there's also the case where they are exactly the same, and I want to know what happens then. So in the other case it is minus. So what happens when we're asking for first number in the cut point? So let's see, let's say that we're asking for position 0. So we're asking for this one here. So that is the case 0 on cut. Yeah? That means that 0 equals, well, no, wait a second, that doesn't equal the cutting point. The place where we equal the cutting point is actually here, right? Okay, so that is position 2, and so 2 equals exactly the cutting point, and then basically it means that this original position is 0. So wait, why am I writing 3? It's 2. So we still do actually 2 minus the cutting point and get 0 as an answer. So if we're on the cutting point, we have to deal with it in the same way as being after the cutting point. Okay, which is the case where the cutting point is before. So before or equals, that is our comparison, like this. And let's see if that works for example 1b. I want to know the sorted output for 1b. Maybe we can print it here like this. So we are sorted here, and now let's say that we want to know what is at position 0, 1, 2. So we should get a 7. And do we get a 7? No, we don't. We get minus 2. So that means that something is probably reversed in here. So the cut offset is before the original position, and then we're going to add to it. And in our drawing, do we do that? Oh no, if the cut offset is before our position, we need to subtract, not add. Yeah. So it means that our original position minus the offset, that is the right answer. And here it's plus the offset. And now we get position 10, that is also not right. So I think there's something wrong here. Okay, maybe I can make my own example where we just have, well, I guess debug mode is gonna help us out again. So 1b starts with a cut of 6, so we could basically very quickly figure out if that is working. Where are we breaking right now? This is part 1 still. So now we are actually handling a cut, I think. Not yet. Let's handle the cut here. Okay. So what we're asking for is the sorted position 2, and that means in this list is going to be number 7, but our current table looks a bit different. And yeah, we don't have a table actually. That's interesting. So the cut offset was 6, and we are looking for, this is not going to apply, And our original position that we're looking for is position 4. Why is that? Oh yeah, it's because cut is actually the last operation that we're doing, not the first one, because we're reversing. So it is a bit difficult to see if what we're doing is correct because we don't have the state of the table as we've reversed it so far. Well, to help us do that a bit more easily, I'm going to create my own example. So I'll call it test1 reverse cut.txt. And so let's say we just do a cut by 6 as well. Or maybe let's do a cut the way I did it in the example. So we have a deck size of 5 cards and we're cutting by 2. 5 cards, and we can just follow along with our example. And we're going to ask for position 0. As you can see here that position 0 should be the number 3. So let's run this, and we do get 11, so that is really off. And did I change my deck size? I think I did. Yeah, 5, okay. So we're starting with a cut, and the cut offset is still 6, but I thought I wanted to make it 2, so that means that I didn't load my example. Next one, reverse cut. Yeah, so our output says we're finding position 3 originally, and that is not right. That is very wrong. So our cut offset is jumping is 2, and it's not less than 0, so we don't have to reverse it. And our original position that we're looking for is 0. The cut offset is bigger than that. That means in our overview here, that means we're going to have to add to it, right? No, it means we're going to have to subtract. We're looking at position 0, and the original position of that after we cut was actually 0 plus the amount of times that we cut, I think. Yeah, so it was a plus after all. So here we have 0, 1, 2, 3, 4. Ah, I think I have off by 1 error actually. So to go from here till here, we need to add 3. So it's plus the cut plus 1, right? And here we have position 0, and it should go to 0. Well, we have position 2, which should go to 0, so here we can just do -1. So for the case where the cut is on the right side, we have to add 1. That is the case here. So let's go over it step by step. We're going to end up in the second part, so the original position is going to be 0 plus the cut plus 1, it's 3. I think that should be correct. And do we get our output also? Yeah, it's 3. Okay. That helps. And now let's try it on example 1b. Let's just run the whole thing. Oh.txt. It says the original card's position was 12, but that doesn't work because we have a deck size that is not 5. And now we say the original card's position was 11. Well, that is definitely wrong. We don't have 11 positions. Let's actually trace how we sorted the cards. So we started doing a cut like this. only half the leaderboard is filled so far. And you're talking about our leaderboard here on Twitch or the global leaderboard? Let's see how the world is doing. Global. Right. So can you see on this screen how many people have solved it? Not really, right? But you can look at statistics. Oh, that's what you mean. So we have 100 out of... Oh man! I think I can probably get on the leaderboard then. But of course, as we are getting closer to the point where people who find the answer will get a lot of people. Okay, so I have to be quick. Nice, maybe I can get points. Amazing. Just by being here on a Sunday morning rather than being super fast. So excited now. That doesn't help. Alright. I think we were doing quite well. We just need to be very careful and look at our output. And let me make sure that the output stays on the screen. So we did only a few operations, right? We're cutting by 2 and then it ends up like this. Ah. Is that actually how I understood cutting? That I think when I said cut by 2, I was cutting 3 and 4 and putting it on the left. That is not right. It should do it a bit differently. Well, this is actually the correct way because I tested it with the examples, so I'm misinterpreting my reverse cut. Let's look at that. So cutting at 2 is something different than what I showed here. Cutting by 2 means going all the way till here, like that. Hold on. Last 2, 3 and 4 should be cut. So that is actually even different. It's more like this. Yeah, okay. But that looks a bit messy. Let me redraw it. So 2, 3 and 4 are going to be on the left in the end. So 2, 3, 4 and 0 and 1 are here. Like this. And that means that our reverse operation is going to be a little bit different. Those lovely off by 1 errors again. And so we were asking our code to show us position 0, which was this one. That should be 2. So for the case where we are before the cut, we can just add the cut. So plus C, and that goes all the way. Hold on a second. What happens if there was another one here, like 5? Yeah? How would that make it any different? If we now asked for position 0, 1, 2, 3, we asked for position 3, then what does that mean if we're cutting at 2? Then suddenly we're on the right of the 2, so to say, right? So because we're comparing with the cut position, which was 2, so like here, so to say. But actually, all of these cases should be handled the same. So we actually have to check our cut position from the right and not from the left. Wow. So our cutting, like our decision tree is kind of correct. So this whole part, well, there might still be one off by 1 errors. I think there are, but regardless of the off by 1 errors, this logic is right. But the cutting position is not counted from the left, but from the right. So that means that we have to always reverse this cut offset. Is again the deck size minus the cut offset. Okay. So the reversed cut offset is that one. And then now we need to look at the edge cases. I think If we do have the edge cases correct, then we can go on and get on the leaderboard, hopefully. So for 0, the position 0, the cut offset is actually 1, 2, 3, 4, 5. So we have 6 cards in total. 6 minus 2 equals 4. So our cut offset is 4. 0 is less than 4. And that means that we're going to have to add to it. And we're going to have to add 4 as well. Because then we would end up at 0, 1, 2, 3, 4. But wait a second. No, we should still add only 2. That's it. We should add 2 only. Okay, so that means our reversed cut offset is actually conceptually different from the original cut offset. And we need to take into account the reversed cut offset like this, but still correct with the original offset. Let's run it. So the card's original position was 4, and we were asking for position 0 in... No, we were asking for position 0 in this list, and we say there should be a 4 there. Nope, that's not the case. So we need to make a few more corrections then. And all we did was 2 reversals and 1 cut, right? No, it was a bit different. It was dealing and reversing and cutting, so it's quite a few operations. And what do we get as an output? Hold on, is this our code? Wait, am I working now? Yeah, okay, I'm working with the example 1b. Yeah. This is the sorted list. I'm going to keep it here on the screen. 1b. This was 1a, I think. And we are going to look at position 0, which should end up in 3. But why do we get 10? We do get a reverse increment of 7. Right now we're actually breaking. So our list, well, we cannot see what our list looks like right now, but technically it should look like this. Maybe what we can do is actually go over all of the lines and every time do an inverse operation of all of the digits and see that we reverse it correctly. So this is basically the function that reverses it, or maybe it's this one here. We want to reverse a single operation, right? With a certain position. Okay, I'm going to extract this into a function. And let's see. We're going over all of the lines, then we're reversing the lines so we get the instructions in the wrong order, and then we're going to get the original position from some input. Okay, so let's call it a reverse operation, which is the line, and we need to give it a sorted position, and that should give us the original position, right? And that function is going to be separate. Reverse operation with a line and a sorted position. And we start with assuming that they're the same, and then we're slowly going to reverse it. And basically that means that here we can kind of just return it. And here we can... Oh, dealing into a new stack. Yeah, okay, we do that. So we are returning also. And here I want to return, and here I want to return. That's it. So this we can now apply to every position in our puzzle input, so that we have an idea of if our reverse operation is working and on which one it's working and which one not. So for part 2, I'm actually going to reverse all of the inputs, but I'm not sure exactly how I'm going to do that. Maybe I'll just make a loop here. So we have our lines, and the sorted position is the one we're interested in, but let's say we would do all of them. Yeah, okay, then we get a new, like, restored line. The restored line would be one where we go over all of the positions for all of the positions in the range of 0 till deck size. And then for each of them we would reverse the operation. So we reverse the operation with the line for position P, and that is what we return. And then we'll say that we restored the line like this. Yeah. Okay. Let's see if that helps. I don't get any output. Why is that? Maybe I didn't call part 2 anymore. Okay, so now we can see how we reverted, and we are reverting element by element. So maybe that's something I want to show. Reverting, oops, element sorted position, and yeah, okay, so we're going to print reversing increment every time. That is a little bit annoying, I guess, but maybe necessary. Oh, I do realize something now though, that if we actually want to keep running this on the whole table, then I think we do need to keep the whole table also. So we cannot actually just run this on a list of range. This is actually a table. So table is going to be a range of 0 till deck size, like this. And then the table is going to be restored like that. Okay. And maybe, why is this not working? We're trying deck size minus original position, and that doesn't work because we say that we have none. Let's debug. So we don't repeat, we just have only one repetition. Maybe I should actually break here. So wow, it's already so sorted. The result is, what is this result? Oh, hold on a second. I think I'm keeping also the result into the line. That is a bit weird. Well, I guess it doesn't matter. Okay. So that means the reverse operation should return the original position if we don't match anything. No, you know what? I'm gonna remove that. That is not helpful. Maybe that's why it didn't work, in fact. So we have it sorted like this, and to reverse it we should get the sorted list again. So what does our table look like now? It looks like 10, 9, 8 until 1. That is a bit strange with the deck size of 10. We should have zeros actually. So our first operation that we restored was reversing dealing into a new stack. Right. So that means that if we reverse, we do deck size minus original position, but it definitely should be -1. So 10 minus 0 would be 10, even though the highest element is 9. So now it should be a bit better. Reversing into new stack, and then we have our restored table, that is 9 till 0. And then what are we doing now? Our line is deal with increment 7. Reverse increment 7. Now we have this line. Do we have it in our original input? Starting with 7, 4. No, we don't. Maybe it doesn't matter. And then we're gonna cut it by 6. Oh, reverse cut offset is 6. That doesn't look right. The reverse cut offset should not be 6. It should be... Well, what was our cut offset? It is 6. And the deck size minus... that's 10 minus 6 should be 4. Ah, okay, I'm not printing the right number. So probably it's correct. So the reverse cut offset is 4. And we restored now like this, and that is definitely not right. How is that? If our original position is before the cut offset, that means that we have to add it or subtract it. Oh man. Let's see again. So, yeah, a lot of scribbling here. Let me just remove that. Yeah, it's sometimes a bit annoying to kind of keep drawing all these things over and over, but I know that if I don't do that, I'm just kind of going in the dark and I have no idea what I'm doing. So it's actually fine. If it takes 3 or 5 times to understand it and to remember it, then it just takes 3 or 5 times. Just have to accept it. So we're cutting here in this way, and then we get 2, 3, 4, 5. 0 and 1 will be on the right. And let's say we're looking at position this one, for example, a nice case in the middle. That is position 0, 1, 2. And that would have original position 4, of course. And 2 is... let's look at the cut offset. Ah yeah, so basically this is the part that we're looking for, not this part, right? So the reversed cut offset is 0, 1, 2, 3, 4, 5 minus 2, which is 3. So position 3 is actually here. But if we include the 3, then we will also keep 5 as kind of being before the reverse cut. So 4 is before the reverse cut, or the reverse cut, and then we're going to have to add the cut size to 4, and that is 2. Okay. So the position I'm just going to rewrite it just to make sure that I get it really right. So if the original position that we're asking for is before or after or on the reversed cut offset, then we're going to add the original position plus the cut offset. We don't actually have to do +1, I think, because in the example we have position 2, and when we add 2 we get 4, which is already correct. Then else, basically every other case, we're going to return the original position. And what do we do with that? So that would be the case here, for example. The reverse cut offset was in fact 5 So the reverse cut equals the size of our deck, which is 6, size minus the cut, minus 1 I think, so it's 6 minus 2 minus 1 equals 3. No, that's not right, we don't have to do minus 1. So basically it's the size minus cut offset, so 6 minus 2 equals 4. That is going to be what we add, or rather subtract from the original position. We actually remove the reverse cut offset from it. So we do minus 4, but in the other case we do plus 2. Okay, that's something I hadn't realized. So maybe that is the final answer, but it doesn't seem like that. We should get, after sorting, what is our answer? This is our sorted list. And actually when I'm asking for position 0, it looks like I'm getting the last item on the list. I'm getting 6. Interesting. Maybe there's something about that. Maybe we have to index from the right, although I'm not really sure why. Let's try out what we get for position 3. Or do we actually get this entire list in reverse in the end? No, we don't. It is a bit different. Actually, the list does look kind of similar. 3, 10, 7, 4. And here we get... where is the last reversed one? 0, 3, 6, 9, 2. Hold on. Let me compare it here. So R is for reversed or restored. So you see that it's actually right, except for this 10 here. So that means that probably we have to do a modulo somewhere. Probably. Well, let's see where we generate the 10. That is not here. It's when we are reversing the cut. Okay. So at some point we are adding 10. How can that be? When we are adding here, for example, let's say our cut offset was at the very end. I'm not so sure, but of course the way to deal with it is basically doing a modulo 10. That would work, but that is a bit of a blind work. Like basically it means I'm not sure what I'm doing. Here we're dividing by the increment. Maybe let's say that we end up having 10 as an output here. Then maybe we should still modulo it by deck size. Let me try that. Which is a bit weird because I am adding already deck sizes as small as I can. But maybe that is the clue. So the restored version is still the same, so this was not where I needed to make that change. And how is the global leaderboard doing? 71 people have solved it so far, so we are still in the running. So where else can we make two big numbers? Numbers that are too big. Here we do deck size minus cut offset. So if the cut offset is 0, well, it's not 0 because I know the example. The example is 6. We should actually be able to see where our code fails, right? Let me run it one more time. So we start with this, and then we should at some point get this list also, right? I'm not sure actually if the intermediate states are going to be the same as the intermediate states in the other sequence. So our first restoration attempt has 741 in it. And do we have it here? No. Well, we do have 741 here, actually. So maybe that is because... yeah, I know. The reversed cut offset. Is that actually what I need to do? Yeah, I think so. I think so. So 741, that is interesting because this is what we get, and then when we cut by 6, we should basically get 741 here. Okay, so that works. And that means that we have a 0 here, but it is changed into a 10. So here, somewhere here, we are creating a 10. And I'm not sure if that's because of the original position we're asking for, or here. You know what, I'm just gonna do modulo 10 on this one. Because it's too high anyway, right? If it's too high, we can do modulo. Well, that is right. And we do get now the original card's position was 6, which I think is wrong. Let's try position 1. Here it says we get 7 as an answer, but that is definitely not right. Even though our restored list is completely correct, how is it possible that we can restore the entire table, but when we ask for a single position, we don't get the right one? Yeah, we have to actually pass the original position here, like that. So we're asking for position 1, and that says its original number was 0. That looks correct. Okay, so now we can actually try it on the entire input. So we don't want to keep a table with the deck size. That is way too big. And we're going to do it with the full deck size. So part 2 has a deck size of a gazillion. Almost a gazillion if you round it. It was this many cards, right? And the number of repeats, we also have to actually specify that. And I haven't tested the repeats at all, but I suppose it will work. Let's see and hope. And we need to know position 2020. And let's run that. Memory error. Where? For part 1. Okay, but we don't want to do part 1. So here it's reversing and doing a lot of things. And let me actually replace print with debug. We have so many statements. Print, or maybe I'll call it log, and then define log as pass or something, so that we don't log anything. Maybe I should do like list args. Okay, let's run it again. So now we log nothing. Oh, but I do want to log here. And that takes a long time, of course, so let's print our iterations, but not all the time, only when we do one, maybe 10,000 steps or something. When we divide by 10,000 and we have no remainder, then we will print the iteration like this, with going back to the start of the line. And then we'll print an extra line so that we can get the output on its own line. Oh, that didn't work. I have to do end equals nothing. So that is going to be running, and I see that there is no output, and that could be that we don't have output buffering disabled. How does that work again? System std out dot flush or something? Oh no, sys dot std out flush. And we don't get any output still. Is that because it takes too much time? No. Maybe I can do sys.stdout.write and just write this piece. We really get no output. And with the new line it would probably work. Yeah, so output buffering is on. I know that you can change that. Here Python unbuffered is on 1 by default apparently. So you would think that it's not going to buffer anything. And I must say that I have done this before actually, and it worked. So why is this not working? Text editor? What do you mean by text editor? Oh, hey Rose, I think probably you don't know what we're doing here. What we're doing here is Advent of Code, and it's a puzzle. And the puzzle is like this. Hold on a second while I run this, because I'm still in the leader. I'm still on track to be on the leaderboard. So we have a puzzle where we have to sort a deck of a gazillion cards according to a specific algorithm. And then my text editor is PyCharm, if that is what you were wondering. I thought you meant to say that we are building a text editor or something. Yeah, well, just in case. So we're sorting a huge deck of cards in a specific way, and then the question is, after sorting, what do you get in position 2020? What card is there? And so I'm now running it, but you can see that repeating it that many times is actually also impossible. So wow, I spent really quite a lot of time reversing all of these operations, and then I find out that it doesn't work, because this is still going to be repeating, yeah, forever. This is going to take forever basically. So what can we do? What can we do? I'm not gonna wait a gazillion hours, of course. Yeah, I'm thinking now. I am running over all of the lines, like every time. That sounds a bit slow. And it seems like I'm not using the deck size. Maybe I want to pass that here also. Well, it is a global, so probably it's already working because of Python just being happy using globals. Deck size. But yeah, this is going to take forever. Even calculating it, I know that there's no point in it. So let's say that I'm doing about 10,000 per second. So that is that many seconds, that is already like a billion years. That many hours, that many days, that many years. Oh, it's not a million years, it's 322 years. So that means if I can optimize it by 100 times, then we can still do it in our lifetime. I don't think I would get a good score on the leaderboard though. So we would have to optimize it at least... I want this to run in like a few minutes at most. So divide by a few minutes, which is 5 minutes. Wait a second. These are the hours, so like this. Okay, so we need to improve the performance by around 122 million times. Okay. Okay. Can we do that? So what it means is that we should not repeat this. I think what we can do is actually figure out that if you run all of those reversals once, then what is the kind of jump that you made? So let me show you what I mean. Yeah, I think I have an idea here. Oh, we have our input list of cards, and we have a certain card that we're interested in, and then after applying all these operations, F, then we actually end up with the card there, right? And now what do you know? What happens? I was gonna say, what happens if you apply those operations again? Maybe you can just reapply the same logic, like going back and forth or something, but no, I don't think that would work. Because we are going to have to figure out where this one was originally, and depending on the cutting and such, it could be like here, you know, it doesn't have to be a repeating pattern. At least that's what I would think. I would think that there is no repeating pattern in it, but maybe there is. Let's actually print where we think that our position is every time that we run it. Where's my code? So every time we found the original position, we are going to print it. Yeah, that's what we'll do. Like every single time. And then maybe we'll find out that there's actually a very strongly repeating pattern in it. Yeah, it looks like that. So we get basically 5298, 5298, 5298, 5298, 5298. So now we know that, and this is a hack. We're going to repeat it. Hold on a second. If we have 5298, 5298, what does it mean? That we can repeat it only... We can repeat it less times. Basically... I'm now actually thinking, what does it mean? Does it mean we can do only 1/4 of the repetitions, or does it mean we have to repeat only 4 times, or do we have to repeat 4 times plus the number that we remain after doing modulo 4 on the input, on the number of repetitions? So let's see what this is actually, modulo 4. We get 1. Yeah, so we have to repeat it once, I think. Right? Oh man. Let's draw it. Okay, so let's say that we have a repetition of 4. That is what we're actually having. So that means that if we have a bunch of patterns here, we have a bunch of positions like this one, it means that after 4 times it's still in the same position, right? So here it's again here, and here it might be somewhere else, and then maybe here, and then maybe here, and then maybe here, and then we're repeating the pattern. Now we want to repeat it a gazillion times, but let's say that the pattern is 4. Pattern is 4, and we need to repeat 5. Repeat 5. So basically it means that we can start at this position and then repeat it only once. Alright? I think what it means is we just do the modulo, and that is how many times we're going to repeat it. And I think the pattern was 4 long, 5298, 5298, 5298, and so on. So this is how many times we repeat it. And original position was 4. That doesn't sound right. Am I using the right deck size? Yes, I am. What number is on the card that ends up in position? Okay, let's see. Is it 4? Nope. If you're stuck, make sure you're using the full input data. There are also some general tips on the About page. Okay. Make sure you're using the full input data. Right, I am using that, right? No? I think so. Yeah, so we're repeating it only once. It feels like not enough. But we did check it, that this is modulo 4. Basically, it's only one iteration. So we can do it a million times, but it wouldn't matter. And am I looking for position 2020? Yes, I am. Any hints, anyone? What do you think, where I might be going wrong? Like, I think my logic is sound. Why would we repeat it so many times? So we need to repeat 5 times in this example. So this would be 1 time, 2nd time, 3rd time, and 4th time. This would be the 5th time. So if we do 5 modulo 4, we get 1. So we have to repeat it. We have to apply the input transformation once. And I'm doing range 0 till 1. That is excluding the 1. So it would repeat it once only. And that means that we are starting here and then going here, and that's it. I do find it interesting that the pattern is so short. I hope that is not a problem. Yeah. So we should get position, and then the original card's position was. And here we say 4. Okay. Do I get the right number of cards? Maybe I have the wrong number of cards. Yeah, my deck size is not correct. Okay. Well, that didn't help a lot. Actually, my deck size was correct. And what does Halley's Comet have to do with this? It's a beautiful comet, though. Maybe it takes a long time for it to fly or something. You still can't find that reverse function for that deal with increment. I think I'll take a break. Yeah, that is sometimes very helpful. And we have now 86 people on the Gold Star list for today. So it's technically still possible to get on the board. Well, that is very surprising. And I feel like I'm there. It's just this repeating pattern. That is the only problem. Let's say that I repeat it like this. Well, that doesn't matter, of course, but I should get something out of it. Well, let's say I do repeat it many times. But let's say I repeat it many times 4, or 4 times 100 plus 1, for example. Do we still get 4? No, we get something else. So it means that despite the fact that it's a multiple of 4, doesn't mean that... Oh, you see? I think I have to repeat it at least 4 times, and I cannot just do 1. Okay. Well, then I'll repeat it 5 times if that is what I need to do. Sure. So now I get 5 as an answer. It's still weird. Let me check if my deck size is correct. Let's reverse the operations and see how it works. Actually, let's log it also. So let's print all of the arguments here and run it 5 times. So you see, card position changed into 2020, reverting the number What is this? Card was changed into position. It's after we... Ah, okay, the new position is actually here. Our original position is now this. That is what it changed into. But why now we have a problem? We cannot take the original position and deck size. What is going on here? Oh, here we have a while. And deck size and factor. Is deck size none? Why do we suddenly get errors? Maybe because I broke something by cutting it wrongly. Oh, I should return it. I shouldn't override it. So I wanted to actually print it and return it like this. So it changed into this one. Then we are reverting this number. And reverting, I think, was... Ah, yeah, okay, that there was a certain operation with a certain position. And then we reverse the increment of 7, and then we get something, we get an offset. Why do we suddenly get position 4 and reverting 4 again? I feel like we're not working with the right data or something. So we reverse cut by this number, and then we'll say position 4. And where do we print it? We're printing it here, right after. We're still asking for position 4. Is it really true? Oh, I know. Oh my god, I'm not running it on the input. Oh, jeez. Okay, that was it. So I think I should run it once and then maybe, no, I should run it 5 times probably. Man. And this is the card's original position. Let's try it. That is a mistake I have made before. That's not the right answer, it's too low. Okay. Too low. Well, I was thinking to run it only once. Now we get a different number. And if we run it 5 times, shouldn't we get the same... Wait a second, maybe our pattern is now different. Hey Kunal Codes, I see you're advertising your channel. I don't appreciate that very much. Please do just enjoy the chat here and talk with people. But I think it's not very polite to try to take people away from your channel. But I am, of course, encouraging people to start live streaming, and that's very great. The better approach I would suggest for you is to direct message other people, or just kind of get into touch with them and kind of make friends, or invite some other streamers on your channel and kind of build some connections. You know, I'll be happy to raid your channel when I'm done, for example. So I'm completely up for that, but this is in general something people don't like very much. We're doing Advent of Code. It's a puzzle game that lasts for 25 days until Christmas, and today is day 22, and we have just shuffled a deck of cards which has a gazillion number of cards. And now the question is, if you would shuffle it according to a complicated algorithm for a gazillion times, then what card ends up in position 2020? And I'm not able to figure that out yet. So I was trying this one, that doesn't work. So if I shuffle, run everything once, we get this. And if I do it... Oh yeah, I remember what I was doing. I was trying to figure out what the pattern was. And so for that I'm going to input the original number and then print every original position and see that there is some kind of pattern in it. And for that I want to disable my logging. So strangely enough, we do get the same output each time. That is very strange. Does it mean that the kind of input that we get on this particular deck of cards is not repeating? Or actually it's kind of static, stable? We do reverse everything, but we always get the same answer. But that answer was not right, it was too low. So it is kind of weird that it goes like this. Okay. Well. So we are running it, and every time we get the same output, as if we have a sorting algorithm that is a stable, that actually doesn't change the number 2020. That is very unexpected, so I think it's probably incorrect. So let's repeat it once and see what happens. So what happens is that we first cut by 9439. That is the last operation we have, right? Then we reverse the increment and we have a new position, and then we reverse cut by something else, and then we're reversing an increment and we get another number, and then we get another number and another number, and then when we're done we say it changed into this. Is that really correct? I want to print a little bit more in the reverting functions, like here for example. And like here. And then let's print it. Log it actually. So we're logging the output of each step, and that helps, I think, to figure out how the algorithm is working. And here also, please. I am overwriting the original position, which is very ugly to do, but for now I will keep it like that. So reverse with increment, reverse dealing into new stack, reverse cut, reverse negative cut into, okay, and opposite cut offset is some other number, and then we get some output. And if any of the lines are different, then what do? We just return the sorted position or something, or we return none and we should get errors. So here, reverse cut by this number, we should, and now we get 9. That seems a little bit unexpected actually. And I think it's because I'm doing modulo 10 here. So definitely modulo 10 is not a good thing to do when your desk table size is actually not always 10. You found, oh gee, you're saying you found your function for reverse deal with increment. Another break now. Thanks for the encouragement. Yes, just keep going. You will find an answer, and if you don't find an answer because you really have tried everything and you don't understand it, then of course you can get a hint and learn from what people are doing. So now I actually get something that is a bit more logical. Yes, this modulo 10 was really, that was really what messed it all up. So it was a silly mistake in the end. So now let's run it many times and see if there is some kind of repeating pattern. That is not that easy to see. How can we see if there is a repeating pattern? Ooh. We can of course keep a list of all of the numbers and see that the first half of that list is the same as the second half, then we found a pattern. That's what I will do. Iterations is an empty list, and after every iteration we're going to append it. And I think I basically remember this solution from the Advent of Code from last year, how to detect a pattern in a list. So we're appending the original position, and then if our iterations from 0 till half of the iterations, so that means that our iterations is also an even number of items long. So iterations modulo 2 is not anything, and the first half, which is the length of the iterations divided by 2, equals the second half. Oh wait, yeah, this is the second half and the first, and then we need to start from iterations, oops, divided by 2. And I do want to double check if that is actually the correct way to write it, just so that I don't have off by 1 errors. So I have a simple case with a repeating pattern of 1 and 2 and 1 and 2. My list length is 4. Who just finished actually? Oh, Emily, nice. So you're also online today and working on this puzzle. Hold on. So the list length is 4, and we want to make sure that list from 0 till 2 equals 2 till the end, yeah? And I think that is the way it should be, because the ending position is exclusive. So here we found the pattern, and let's print it. Pattern length is basically this, if it is correct. Pattern length is, that is cool if we can figure that out. Well, so far we don't. I am breaking, but am I breaking correctly? Maybe I should just return instead. We're printing a lot of stuff. Maybe it's a bit too slow actually. So let's not print everything, and let's just keep running it. Ooh, we've done already a lot of iterations. By the way, if we found the pattern, we don't have to run it again with some kind of modulo. We can just stop or something, no? But you only know the pattern when you fully completed it a second time, right? So we'll have to run it at least twice. And then, if we've done it so many times that we've repeated the pattern twice, but then we still need to repeat it the number of times that we overshoot the pattern length. So let's say the pattern is 3 long and we need to do 7 iterations. Then after iteration 6 we found that we have repeated the pattern twice. Hold on, let's say that we need to do it 10 times and the pattern is 3 long. So when we have done it for 6 times we found the pattern, but we do need to do 10. So we can now do 10 modulo 3, and that means that there's 1 remainder, and we have to do it 1 more time. So basically, if our number of iterations modulo the pattern size equals the repetition requirement modulo pattern size, then we can break, right? So we shouldn't break here actually, we should keep going, but we should keep the pattern size. And let's assume for now that the pattern size is the same as the deck size. Does that help? Maybe the pattern size is none. So if we have a pattern size, it's not none. So that means we're also going to store it. Oh wait, I call it pattern length, but maybe... Yeah, okay. I'll call it pattern size, that is the one where we are actually storing it. Pattern length. And we don't return. And if we have a pattern size found, and if we have done... now we're adding and adding to iterations also, and that will take a very long time, so I don't want to keep doing that. So as soon as we are finding the pattern, we stop appending to the list. If pattern size is none... By the way, I just realized that maybe there is no pattern. That is possible. That is very possible. But if we have a pattern and the pattern... the number of iterations we've done, that is I should be incremented by this point. So we've done one iteration at this point. Modulo pattern size equals the repetitions modulo pattern size. Then we can stop. Return. And we can print the position. Well, we might need to try that out on the example. So our example has this example 1b. I remember that one was repeating. Although we don't detect any repetitions. Let's print every part of it. No, let's print only the positions that we find. Like, not this. Here. Yeah, okay. I don't see that happening actually. I don't see that working. Actually, what we do know is that once we find a position twice, then we have a repeating pattern, because this is completely deterministic. So actually we don't have to keep a list and track the whole list. We just need to figure out whether we've seen a position before or not. So instead I'm going to keep a list of positions as a set, and every time I'm going to add it to that list. And if we found a pattern, that basically becomes a very different check. So if our original position is in the positions, of course I should add it after this check, then we found the pattern. And now we need to know the pattern length. And the pattern length is basically the moment when we find the second one. So the pattern length is our current iteration. Let's say that we have a pattern that is too long, the same as here, so 1, 2, 1, 2, and that means we can detect the repeating pattern already here at iteration 3. So we have iteration 0, 1, 2, and 3. It's called iteration 2, so our pattern length is actually 2. It works out quite well with the 0 indexing. So the pattern size is I actually. And then we don't need to look at any lists anymore. So this list can go. This list can go. I do want to kind of have a breakpoint here to see that it is working. And so far it's not helping a lot. Maybe we can do a deck size that's a bit smaller. Let's say our deck size is still the same as it was. Maybe we have repetitions. Yes, we do. So 5003 items actually. I'm going to have to take a very small break for a few minutes. I will see you like in 5 minutes, so do stay on the stream if you're interested in seeing the rest. Alright, there I am back with a sweater on because it was getting a bit cold in here. So, I think we have a solution. We have something that I think is conceptually right. So let's see here, we have a pattern length of 5003. Let's see if we get the same position after 5003 iterations again. So I think now where we are going to break, like we have a breakpoint here. So I actually don't want to break. Yeah, here I'm breaking actually. Well, let's see what happens. Let's actually run it. Continue. So it still says that we found a pattern. Yeah, that's of course logical because we wanna not keep the pattern every time, because of course we are going to repeat the pattern at every position. So once we find the pattern, then we don't want to keep overwriting it. So if pattern size is none and the original position is in the positions, then we can run it. And let's continue after the first pattern was found. And then we run it a bit more, and then we get this as an answer. So let's do it now on the real deck with the real input, or maybe the number of repetitions is still correct, yes, and the deck size needs to be larger and the input needs to be the original input. That's probably going to take a long time still, I think. So let's run it like this. We print every 10,000 steps, like that. And I don't know how long that's going to take actually. 10,000 steps already takes a long time to print. I do want a little bit faster feedback than that, maybe every 1,000 then. And also, I am curious if I can optimize this at all. We can figure out what makes it slow, but also we can just run it for some time and see. And I still don't know if this repetition pattern thingy is correct. I think it's correct, but I'm not entirely sure. I haven't tested it actually. I should kind of test it on example 1b. But let's run this for a minute or so. So in the meantime, I see the following people having completed the second part, and it's Alex, Arcanian Archer, and Hans. So good job on that. If you're still on the stream, maybe we can start sharing some code for the first part, if you are willing to. Because this is just running in the background anyway. I'm not sure if it's going to complete. Well, how do you know it's going to complete? You don't really know. Yeah. Hey EP Knothead, what we are doing is we're taking part in Advent of Code, and that is a puzzle event that takes place between December 1st and December 25th. Every day we get a puzzle, and here is our calendar. So if you complete a puzzle you get stars, and if you're the first one to complete it you get also 100 points on the global leaderboard or something like that. And we are all trying to be as fast as we can. Today is day 22, and our mission is to implement a shuffling algorithm. So let's say we have to deal a deck of cards, and you can do cuts and you can reverse it, and you can deal the cards by skipping steps. So you would take the first, the 7th, and the 9th card, for example, or well, consistent steps, that is. And so actually we have shuffled a deck of quite a lot of cards, this many cards. I don't even know how to pronounce that, so I've called it gazillion for now. And we need to apply our shuffling algorithm also a gazillion times, and then figure out what card is in position 2020. And I think I found some optimization, but I'm not entirely sure that it works. And my optimization is assuming that when you apply this shuffling algorithm many times, that you're going to end up repeating yourself. So basically that after running it maybe 10,000 times, you end up having the card in the same position as it was before. So I'm trying to optimize by detecting this, and then what? And then let's say we have a repetition of 10,000 times, but we need to actually do 11,000 repetitions. Then we still have 1,000 left, so I would also do the last 1,000 extra. And it's running, and it's very slow, and yeah, I don't know how long it would take. And Alex, you deleted your first part because you redid it like you did the second. Oh yeah. Yeah, it's pretty cool. Actually, if you like programming and you like some puzzles, you can join, because it doesn't matter if you're late. You can see here in the global statistics overview how many people have completed every puzzle so far. So puzzle 1 was completed by 80,000 people, and then there's only the first part that was completed by 10,000. And you need to learn how to code. Okay, so if you have like 0 coding experience, I think Advent of Code is going to be really challenging, because it does require quite advanced programming approaches. But you can start with day 1 and see how it goes. Day 1 is a bit more complicated than day 1 of last year. I I think maybe last year was a little bit easier than this year. So you could also look into Advent of Code 2018. And the way to do that is to go to Advent of Code and go to 2019 and replace the last digit. Then you can see also what I did actually. You see that I didn't do all of the puzzles, I just did a few of them. You can also click on events. So, here, you're right. Yeah. You can even go back all the way to 2015. Oh wow, what a nice tree. I must say that the ASCII art is improving. Look at what we have now. Well, okay, it's still pretty simple, but it has some colors in it and I think it adds a lot. And last year it looked like this. Oh yeah, and I think you only get the colors when you actually finish it, and I didn't. So that's why it might look a little bit more simple. I'm not sure. So here we have some bright colors, okay. You understand some of the basics in C, and kind of the ideas behind it. Okay, yeah. Well, you can try it, of course, and you can do this in any language. I'm just doing Python because Python allows me to try out many different approaches quickly. And it's not requiring me to do a lot of type definitions and kind of formal specifications. And it does bite me in the ass sometimes because I break my code in unclear ways. But so far it's been quite alright doing it in Python. Okay, so Alex, can I ask for a hint? Is trying to search for a pattern a good idea, or am I completely on the wrong track? Yeah, go ahead. So the link, I'll just post it here on the chat. That is the link. And you can sign up with GitHub or with an email, I think. It's still running and running. You're not sure if it works and how long it would take, but that's not how you did it. Oh man. Okay. That's not how you did it. Then there may or may not be a pattern. So I think that means for me, trying a different approach can be useful. I'm going to commit this because I'm probably going to butcher up the code we've made so far, and what am I doing? I'm running it rather than committing. How many cards in the deck again? A gazillion. Bigger than you can count and bigger than you can pronounce. Oh, wow, okay. It runs in 0.009 seconds. Okay. So the number of cards is this. That's the number of cards. And we're going to have to apply our shuffling also a similar number of times. I'm not sure if it's the similar or not, but it's also huge. So if you can shuffle, let's say your shuffling is so fast that you can shuffle 10,000 times per second, then you're still going to take 10,000 times per second, then you're still going to take 300 years to solve it. You won't be able to find a pattern based on a shuffle until you hit like that number, but with the exclamation mark at the end. What do you mean with an exclamation mark in the end? By the way, our shuffling is deterministic. It is completely deterministic. So, okay, you know what? I'm going to think about another way to solve it. And basically, maybe it's something about running the shuffling algorithm a certain number of times in a row. But I think I couldn't even do a single iteration, you know that? I think so. So I was let's try part 1 on the input here with this deck size and see if that works. Yeah, I got a memory error. That's why I can't store a list with that many cards. Yeah, factorial. I don't know. I don't think that there's a factorial thing in here. Not sure. So let's say that pattern repeats every 8 shuffling iterations, then you know you will get the same number in 8 times. So basically if you keep all of your numbers so far and you find it after 8 times again, then that's just 8 iterations. Well, okay, let's go back to the drawing board, as they say, and literally. So we do apply our input many times, and I cannot actually run it on my list because of memory issues, and that is a lot of cards indeed. And I was thinking if instead of keeping all of the cards in a list, I can just remember for each card where I shuffled it, but that doesn't make sense because then I'm still keeping an integer for every card. A different data structure probably will not work either. Maybe a byte array or something. So let's see how many bytes we would need for something like this. So let's say we are storing this many integers, and each integer is 64 bits. Then that is this many bytes. That is this many kilobytes, this many megabytes, this many gigabytes. So it's 800 gigabytes, okay, of memory. Not gonna work also. And your previous approach of calculating backwards was good. Okay. Maybe, but yours ran in like a few milliseconds. I am calculating backwards. Well, if I would repeat it this many times, it would still not work. Yours takes log iterations. Well, maybe there's something about caching or something like log iterations time. Okay. Well, what's the log? Okay, so that means if you're thinking about log, it's not the same as square root actually. So if you do 10 times, or I guess 2 times as many iterations, you're going to take +1 extra time or something. Or if you're going to do 4 times as many iterations, you're going to take twice as long instead of 4 times as long. So that means that you can kind of factor this in some way. Maybe we can. Maybe we can. No, I don't get the hint, I think. I'm thinking if we can break up the problem in some way. Like maybe we could... well, you know what, I'm just gonna keep it running for now, in the background. Just in case it works unexpectedly, but I don't think so. And also, I'm going to do a... what is this? A profiling session. And see if we can get some hint into why it's so slow. How much of a hint do you want? I'm not so sure. Like getting the answer right away, of course, is less fun. Maybe I'll wait for the hint a little bit. Or maybe not. So I am guessing that you're thinking about splitting up the problem, dividing it in some way. And I'm thinking about, well, I am doing the reverse, and you said that this was correct. So basically I just need to look at position 2020 and reverse from there. And how can we make it faster? We have a lot of cards. Does it matter how many cards we have if we are only looking at one position? Not really, actually. It doesn't matter at all. Because we're only jumping between the bounds of the number of space cards. That's all we're doing. And if we are going to do it many times, then we do have an issue. And it's also not the case that we reuse those shuffle algorithms, because well, because of what? Well, oh wait a second, log. Actually, log, I know what that is. It is an indication of a binary search, perhaps. Perhaps you're doing a binary search. The reverse operation takes the most time in my code, and out of that, it's the function called search. It's the regex that takes the most time. Oh no, really? I'm doing a regex search for every line. That's crazy. Okay, I see. That is also very slow. So I will actually get that regex out of there, and I'll keep a list of, what shall I do, operations or something. So we have few operations. We have deal is 0, and then we'll have, yeah, if you get the math right, regex won't matter. That's something I'm also thinking about. Like, it's the same with my breadth first search algorithm. I was trying to optimize it by improving my heuristic. Didn't help at all because I was doing the basics wrong. I was not checking for if I visited that location before adding it to my list. Then you can try to optimize doing a million unnecessary things, and it's still going to be a wasting time. So I'll take that advice and not try to improve my regex function. So if that is not the deal, then we are going to not parse our input that many times actually. So maybe binary search is something. How could you know? Well, if we could try a random card and figure out if it's too high or too low, that could help. That could help. That could help a lot. Yeah. Okay, so let's say it's card 1. We'll apply the operations to card 1 only and see where we end up, and do we end up in possession 2020 or not. Then we'll try another card, something like that. Well, after looking at the solutions thread, you've determined that you have to be a mathematician for this part too. I don't know. Well, Alex is one, and he did solve it. And going in the reverse direction is correct. But you know, there's the thing about a binary search. Well, you didn't say you were using binary search, but I'm interested in considering the possibility. That means that we have our input and our output, and we want to find one that ends up here at position 2020, and we'll just try one, and then let's say it ends up being here. That's wrong. We cannot say, oh well, it was too high and therefore we need to now look at this part, right? We don't know that at all. We don't know. Well, in some way we cut this thing up in many pieces, right? So then we end up having like this part on the left and then this part on the right. So that is reversed. And well, we could now. Well, maybe what we could do is that we also have to repeat the algorithm many times. So I don't get it. Is it still running? No, it's not running. Okay. Well, Alex, do you have another hint for me that is going to help me? Are you using a binary search? Can I ask that question? Don't just do it for 2020, do it for position X and calculate the initial. That's fine. That's okay. Thank you for the hint. Calculate the initial position as a function of X. Oh. Okay, right, so you're basically, yeah, okay, I see what you mean. But then it's still gonna be slow, no? So basically what you're saying is, you know where every element in the list will end up, right? That is your operation. After applying the entire function. And then you can apply that operation many times, but you're still not gonna apply it a gazillion times, right? I suppose. Well, if you know the mapping like this, then you can also reverse it. That means you can go from 2020 up till here, and then, right. Yeah, no, but that's what I was already doing. So you go here, and then you figure out using the map where you need to go then. So for example, you had an arrow like this, for example, or maybe like, no, you cannot split. We cannot split. So then you basically go again to the map and go up, and you're here, then you go here. But that you need to do it times a gazillion. Oh, I'm drawing again without showing it on the screen. Sorry for that. Well, I'll just repeat what I was doing. So I said that you have your input and your output, and you kind of keep track of where all the inputs are mapped to. That's your function, which you are going to repeat a gazillion times, like this. And you can kind of backtrace it. So you calculated your 2020, and then you're going to re-go over the map this way, and then again this way, then a million times. But that is the point. Doing that a million times is the slow part. And let me reread your hint again. Don't just do it for 2020, but do it for position X and calculate the initial position, one iteration, as a function of X. Yeah. So, is there some kind of system in it? Is that it? Some kind of system? Okay, so I need to kind of make it into a logical function. Maybe I need to use algebra for it. Function is very simple. Okay, so I have to show to look at what the function looks like. So let's just try it. So we have here all of the lines, and after we run all of the lines, we do get a list of a mapping kind of. How am I going to do that? I'm thinking about printing the original position and the other one. So I'll print here the original position without the line ending, and then I'll print again original position, which is now changed. So we have like this. Okay. And let's run it and see if we can map it make it as a function. So here's our output. It's a lot, and we need to kind of see if there's a pattern in it. Maybe what if we would actually print it like side by side and put it into Excel and see if there's some kind of plot that we can make out of this. Oh, no way. Hold on a second, what am I doing? I see here that the second one is the same as the previous one, but I think... No, this is not right. I should do it for position I and not for just one. Okay, so I should go over the entire table and print the new table, but that is too much. Maybe I'll make a separate test. And the function is very simple, and you doubt that you can see the pattern though. But maybe we can calculate the pattern. Let's see. So for line in lines, we're going to reverse the operation. Let's do it for every position, maybe the first 100 or so. And then apply all of the operations there for line and I and the deck size, which we have. New position like this, and then we'll print it. Right, and the position is I. We'll pass P and override it every time. And the lines need to be reversed. And then we're going to print both I and P with a string formatting operator and see what it looks like. Well, yeah. I don't see a very strong pattern here. Yeah, so you think no one would be able to see it? Well, what else can we do? The ending digits are even, odd, even, odd, even. That is something. We have one digit. And then we have even, odd. Even. Okay, so there's no pattern in that part in terms of even and odd. Even. Well. Let's try. I actually didn't understand exactly your hint. So I traced back the original position for every table point, but how does that help? So if I know the original position of the first element in the list, then I know it is somewhere in the list. And then I cannot keep it because that would take too much memory, and I cannot keep it, so I should I shouldn't store it. Can I use it right away? So let's see. You need to find F. And how does it help so F is the function that, let's see. So f is the function that calculates the initial position, right? Huh. In G you're stuck, but you're fine on your own for now. Can't seem to get the reverse of one loop right. Trying examples now. Yeah, definitely work on those examples. I really needed the examples also to figure out how it works. So just keep trying slowly and carefully. So what is my function right now? Right now my function is this whole thing. It's reversing one line and then it's looping over all of the lines. So, wait a second, I do get the hint. And it's still going to be slow, right? Yes. So this whole thing can become a function. But it should be a function and not a map. So I cannot memorize it. Just have a bit of water. Because it's now getting hot actually. So it is really simple, you're saying. Basically it means that we can look at all of the lines in our input, these lines, and that would completely determine all at once our output. Yeah. We need to go in a bit. Okay, well that's fine, of course. We all have things to do. I don't. Lol, no I do. I wouldn't also continue till forever. But I am willing to give it a little more of trying. So thank you Alex for staying on and helping me out here without spoiling the answer. I appreciate that very much. And maybe we can look at the solutions tomorrow or in one of the other days. And by the way, I will do a few more streams after Advent of Code because the puzzles take up most of the time now and it's still fun to share code. So do keep joining and keep following me even after Advent of Code. Okay, I think I was saying that I was gonna commit this at some point, and I think I did, but now I want to commit it again. Yeah, you're welcome. Have a good day, have a good Sunday. So day 22, part 2, work in progress. So I think I kinda get it. So let's look at what happens when we revert an operation, excuse me. So let's enable our log function a bit, like this. And we'll reverse an operation and let's run it. So you see here that we do a reverse cut by this, and that means this is the new output. And then a reverse increment. So basically what I'm thinking now is that if you do a reverse cut and then you do an increment, like a dealing with an increment, basically what you're doing... What is the difference between these two numbers? It's a huge number actually. So they end up in being in completely different positions actually. Yeah, I was thinking like, you know, if your operation is like move it 2 right and then move it 5 to the left. Basically it's the same as moving it 2 or 3 to the left. So if you could combine your operations into a more simple operation, that would work. And Alex is hinting that the operation is not that complicated. But is that really the case? I'm not so sure. So we are printing everything in the end. Hold on. So for 99 this is what you get. Well, don't feel like that is helping me. At least I'm not getting there. It's not a multiple or anything. anyone else in the audience who has some idea? Maybe Arcadian is on. No, Arcadian is not in the chat, I can see. And everyone else that we know, Emily and G are still working on part 2. So I cannot ask for any help there. And how is the leaderboard? Have we found 100 people to solve it yet? Yes, we did. 246 people have solved part 1 so far. That is a lot less than what we usually have in a few hours of time. It means that this puzzle is hard and that it's Sunday morning. A bad combination for Advent of Code. Yeah, you know, actually I'm going to leave it at this. For now, I will give my brain a bit of a break and see if I can come up with some better solution. I still have day 18 to solve also. Although I think I know what the problem is, it's related to my breadth first search, and I just implemented it in a bit of a messy way, and I think there's just an implementation error as well. So I will re-implement day 18, and if I have a chance I'll make a video explaining how I solved day 18 in the end. It is a very hard one. If you look at the global board, well, day 18 does have solutions. Not as much as the 17 and 19, so it's an indication. Hey Justin, you're missing the exact same stars. Wow. Maybe you're a follower and you found all of the solutions with my help. Or maybe we have the same skills and the same lack of skills that makes us get stuck on similar problems. So also day 16 part 2, I haven't finished that one. The one with the FFT. It's also a kind of mathematical algebraic sort of thing. Well, that is fun. So maybe once we solve day 22 part 2, then we can get together again and share. Maybe you would solve it in the same time as me as well. Let's see about that tomorrow morning. Well, that was it for today. I wish everyone good luck, and Justin too, welcome on the stream. And if you want to be on the leaderboard, I still will give access. The leaderboard that you see on the top here, it has an access code, and it is, let me see if I still have it correctly. I can copy it from here actually. Here we go. Yeah, AG, I'm leaving already. I think I do need a bit of a break, and I don't have any good ideas right now how to solve it, and I feel like it might help if I just take a bit of a break and give my brain some time to come up with some creative solutions. So you're welcome. See you all tomorrow, and let's also enjoy the weekend and have a great chill out Sunday, or do something fun or productive, whatever satisfies your day. See you tomorrow.